So, good afternoon all. Welcome to session 11. So, we have two more sessions remaining. So session 12 and the extra session of it. So, in this session, we will mostly discuss about the final refining process. Okay, and the refining process of few metals that we have missed in last session. And then we move on to our refining or the secondary refining process. Okay, so following that we will discuss bits and pieces of hydrometallurgy, and then we will end our session 11. Okay? So now let's discuss about the zinc production. Okay. Now let's talk about the zinc refining. First, let's talk about the zinc refining. Now, how the zinc refining happens? Now, as we have discussed before, the zinc, the extraction of zinc from the ore is mainly done by the hydrometallurgical process, not the pyrometallurgical process, because of the amount of assay or the assay that present in your ore. So, if, for example, if still we are following your pyrometallurgy, then what we should do? So for that, the first process is the precipitation. Okay. Now how do? We precipitate impurities. From your liquid pool or from your melt. Or you can do, because the zinc has the low boiling point, or you can do the fractional distillation. Okay. Now, what do you mean precipitate? Precipitation is nothing but you are attaining a supersaturation state. That means everything can be dissolved, not everything. So some things, for example, if you have a solution here and it contains B also. So there is a limit of B that can be dissolved in A. Right? The same goes for sugar solution. If you go on adding sugar to your water solution, the sugar at certain point the sugar will stop dissolving in it. So that is called the saturation limit. And if you go beyond that, that is supersaturation. Right? So above saturation limit, you will have precipitation. The same we are trying to do it. We are trying to maintain a condition such that the impurities comes out. Right? So for that, what we need to do, we need to have a phase diagram. So let's say, and again, what is phase diagram? In physical metallurgical definition, a phase diagram is nothing but it tells you the distribution of equilibrium states for a given variables. Okay. So again, in more simpler form, so phase will give you a spatial distribution. So in phase diagram you will have a graph. So graph is normal thing. Okay. So let's say it is a graph between the temperature and a composition. Okay. Now this graph will give you the spatial distribution of the phases. Spatial distribution means nothing but where the phases are present. Okay. So suppose if I have my zinc, right? So let me check whether it is recording. Yeah, it is recording. So if you have a phase such that it is stable at low temperature, but it is not stable at high temperature, that means the solubility limit will go on decreasing when you increase the temperature. Okay? So this is the amount of impurities that can be allowed at different temperatures. These are the values. That means the composition of the impurities will go on decreasing. So that's why we do our precipitation reaction. So whenever we try to heat our zinc bath at 450 degrees centigrade, it takes time because the diffusion needs to happen, right? So that's why it takes 1 or 2 days. So whenever you try to do it, you have a top layer and middle layer and bottom layer. Okay, so the top layer mostly contains 99.5% of zinc and the remaining lead. Okay? And here you will have intermetallic compounds, or you can let's say you can have even, so you will end up with dross. Again, I have told the difference between the slag and dross. Slag is your homogeneous solution of oxides, right? But your dross is the heterogeneous solution. That means you have both solid and liquid. Okay, it's more like a paste or semi-solid thing. So that's the difference between the slag and dross. Dross contains both the solid and liquid, but in slag you will mostly find the liquid solution of oxides. Some other things will also be there. So that is the difference between your slag and dross. And the middle layer contains your dross, and the bottom layer contains mostly lead impurity, right? And some amount of zinc. Let's say 4%. Now, yeah, this happens batch wise. You continuously try to remove and add things. Okay. Now, this is about your zinc refining. A fractional distillation is straightforward, right? So, because you are distilling at different temperatures. So, all we are trying to do is we are trying to play with the physical properties of your melt. So, that means the impurities may melt at some temperature, or your zinc will have some boiling point, impurities have some boiling point. So this difference we are trying to play, right? Now the next is the removal, the precipitation of let's go with the zinc refining, tin refining. So what's happened in tin? So in standard you will mostly find in tin ore you will mostly find many type of impurities. So you need to undergo different process, right? Because different elements have different properties, and if you have more amount of elements, then you need to take care of more amount of those impurities, and you need to implement different process, right? So it happens stepwise. The first one is you want to remove iron, because tin ore contains a huge amount of iron. So how does this thing? Now it is removed in two steps. First one is dross formation. Another one is matte formation. Now again, dross formation, what you are trying to do, dross is nothing but we are forming solids. So if you want to form solids, that means again we are trying to precipitate something out. And if you are trying to precipitate something out, that means there is some intermetallic that has been formed, right? So that intermetallic is FeSN2. Right? Now again, people ask that what is intermetallic compound, because it is a very much important compound when you are trying to deal with, even if you are trying to deal with steels also you will find an intermetallic compound, which is Fe3C, cementite, right? So the intermetallic compounds are nothing but those metallurgical compounds. Obviously, they are metallurgical compounds which have a long range order, because they contains long range order, and apart from that, they have very precise stoichiometric ratios of metallic elements. Metallic, you can take non-metallic elements also. Okay, so they have stoichiometric ratios, and the other definition you can use is that the free energy is very sensitive to composition. So most of the alloys you find, when you draw a diagram between the free energy versus composition, you have a parabola like this or a hyperbola, and it is, good at a long range of composition. But when you come to intermetallics, because it has a different composition, right? It follows a very strict stoichiometric ratio. The free energy curve will look like this. it is very steep apart from that composition. So this definition also you can use. Yeah. So this is what we do. We decrease the temperature. We maintain some temperature. That means the cooling. You do the cooling such that the FeSN2 iron tin comes out. Okay. And again they are taken out. Right. So. And this dross is again led to your reduction furnace. So to recover tin, that means you react this guy with tin oxide, you will have tin plus FeO. Right? So this is what happens. Now whatever the iron that is remained, you add sulfur, so that iron will react with sulfur to give paste. Okay? Iron sulfide. Now that will come out as a matte. Again, we know the difference between slag and matte. Matte is mostly the mixture of sulfides. And the next is removal of your antimony and bismuth from this guy. Right. How do you do that? Again, you form dross. How? So you form dross by adding aluminium. Aluminium will form aluminium arsenide and aluminium aluminium antimony. So, and the final one is bismuth. Bismuth you remove by adding barium or magnesium. Okay. So, the next one is the chemical transport. Now, the last process is the chemical transport. There are three processes which we can separate, do the refining. One is your precipitation, two is your fractional distillation, and three is the refining. Right. So, refining by chemical transport. The third one, sorry, I just said refining, so it is totally refining by chemical transport. Now, what do you mean by chemical transport? Chemical transport is nothing but you are taking it from your liquidment and you are transporting it to some other place, right? So you are just taking out from your liquidment, right? So this happens when your either metal or impurities form volatile compounds with some reagents. Okay. So that's the main thing behind, or the main theory behind this chemical transport. So either your metals or either your impurities should react with a reagent and become volatile and move away from your liquid bath. So in most of the cases we deal with the metals. Okay, so the metals will react with your some gases and or the reagents, and they form volatile compounds, and these volatile compounds are again undergo decomposition, because we do not want those reagents still attached to it, right? Because we are, our final goal is to get your pure metal. So yeah, they again undergo the decomposition, and you finally end up with your pure metal. So that means your metal is transported from your impure solid, or you can say your liquid bath, right? You are purging some reagent gases, mostly gases or reagents, and they become volatile, and finally again they undergo decomposition. And this again gases or reagents are used repeatedly. So once you separate, you are done with the impurities, and here after decomposition you will end up with pure metal. So if you are taking gases, then the most famous one is the carbonyl or SIBO, where you do the purification of a nickel, which is the Mons process. And if you take iodide, or that is called as a Van Arkel or de Boer process, which is used for refining your titanium, zirconium, hafnium and thorium. Okay. And there are also halides that can be used. So it depends upon what type of reagent you are using, whether a gas or a liquid or a solid. Now coming to the refining with the carbon monoxide. Let's say our gas is our carbon monoxide. Carbon monoxide is nothing but when you combust carbon in the presence of oxygen at high temperature, it will give you carbon monoxide. Okay. This is the final reaction, but actually what happens is the carbon will react with oxygen to give you carbon dioxide, and again this carbon dioxide is not stable, so this carbon dioxide will again react with your carbon to give you carbon monoxide. So this is what happens, and when you add this or when you subtract this reaction, you need to add. So when you add these two reactions, the CO2 will go up, so we'll end up with 2C plus O2 gives rise to 2C. So yeah, so this is the reaction you will finally end up with. And you store this CO, and what we are trying to do is so first this carbon monoxide will react with some of your metal, and it will form metal carbonyl, and metal carbonyl depends upon your coordination number. Okay, so yeah, the coordination number of your metal, and the transition metals can easily form this carbonyls. Why? Because of this D block element. Right? There are so many lone pairs of electrons, and also your D block. Yeah, so many lone pairs of electrons is there, so that's why that can be used to form carbonyls. And also there are some empty D shells also, but again that can be helpful in forming this coordination compounds. Right. So yeah, the formation and the decomposition temperature, the range is wide. So that's why people try to use this thing, carbon monoxide, to form as a chemical transport. Okay, and the next one is, so for example, let's take nickel. Nickel will react with carbon monoxide to give nickel carbon. So this will form, and again this can be so it is boils at 43 degrees centigrade, and again it can be decomposed. Okay, so yeah, we can even use for iron also. Iron can react with your carbon monoxide and from iron carbon, and also please keep this in mind, the formation of carbonyls is not again restricted to the action of CO on the metal. Okay. Even you can directly form a nickel carbonyl again you need a basic medium to form this. Okay. That means my nickel sulfide will react with carbon monoxide under the basic conditions to give me nickel carbonyl plus sulfide plus carbonate plus 1. And also chlorides, if some chlorides can also be reacted, or some oxides also can be reacted. So rhenium oxide can be react with carbonyl to form rhenium carbonyl, one thing, plus carbon dioxide. Okay, so yeah, and the next thing is where these reactions happen. Let's talk about the carbonyl nickel refining. Okay. Now, so this process where we use carbonyl to react with your nickel of a liquid melt to form nickel carbonyl. So this was first done by the Mond, so it is called as a Mond's process. Or you can directly take, if you are trying to do at room temperature, or if you are trying to do at 80 degrees centigrade, and obviously you cannot have nickel melt, right? So then you will have nickel, you can have powder. So because you need to have reaction, right? If you have a bulk compound, then for example 3 mm 4 mm powder particle or 3 mm 4 mm particle, then if you react it with carbonyl, it still happens, but the surface area that is available to undergo the reaction is small. So that's why if you have more amount of fine powder, then the finer the powder, the larger the surface area. So there will be more reaction for your nickel and carbonyl to happen. And as we have said before, only the small amount of iron will only undergo the reaction to form iron carbonyl, and the other impurities remain as it is. So that's why we use this process. And again, this nickel carbonyl can be decomposed into nickel plus carbon monoxide. If you heat it at 180 degrees centigrade, this can decompose, but this needs a seed or nucleation seed. That means you need to have a pure nickel on which this decomposition will happen, and the nickel layer will form. But the iron carbonyl will not undergo the decomposition because it is stable at that temperature. So this can be collected. Okay. And this can again be cooled to get iron carbonyl. Okay. Again, the decomposition of the carbonyl, wherever this is the decomposition that we are trying to see, will happen in furnace, right? So the initially when it was done in electrical furnace, okay, electrically heated furnace. So you have a fine powder, and this fine powder will react with your carbonyl to form metal carbonyl, and this metal carbonyl will be decomposed. Yeah, if you want to like have more and more amount of the impurities, then you can do many passes and many decomposition, and you can even end up with the larger particle size also. So you can have a big pellet because this keeps on adding and like depositing, right? So it will become big, and you will finally end up with a pellet. So that is about the Mons process. Let's move on to again you can see there is a larger decrease in entropy, right? Because 4 moles of gas is converting into 1 mole of gas, right? So that means there is a large decrease in entropy, right? So that means this process will shoots up and become non-spontaneous. Okay, so that's why we try to increase the partial pressure of carbonyl to even get it at high temperatures. So that is one point you need to remember. Now, so let's write the equation, the delta G equation for this guy. Okay, so delta G will be equals to delta G naught plus RT log is the partial pressure of CO, which is taken as 4 times sine. Partial pressure of nickel carbonate divided by partial pressure of carbonyl power 4 times activity of nickel. And because nickel is our main solution in the melt, we can take it, even though it is impure, we can take it as 1. Why? Because most of it contains nickel. That your melt is mostly contain nickel, right? So yeah, it is towards the solvent end in your Raoult's law also, right? Because in solvent end you can see, even this is your ideal Raoult's law, and even if you do some negative deviation here and there, but you will finally arrive to the ideality. Why? Because you are going into more and more pure direction. So you can take it as 1. Okay, it's not to worry about more about it. So here you can see the partial pressure of NaCO4 divided by partial pressure of CO. So for this to be positive, let's say if I try to increase the partial pressure of CO4, then what happens? This number will go down. That means this number will be negative. Okay, that means the ln of some point value will always be negative. So this term will be a negative term. So that's how you dominate this delta G naught value at that temperature. Okay, so higher the negative this term goes, the higher this term goes negative, the better will be your delta G, or the better will be your spontaneity of the reaction. So that's why if we increase the partial pressures of carbon monoxides to higher pressures, you can do your reaction even at high temperatures also. So that's what we see in the nickel carbonyl. So this is just a schematic. This is how the graph looks like. So nickel carbonyl. Oh. So if I So if I try to increase, this is my temperature. This is my carbonyl percentage. This is my carbonyl. Okay. So yeah, this should be the nickel carbonyl, because this graph is the amount of percent formed. This is the 100% that has been formed. So if I try to increase my pressure, okay. So the temperature. So this is for 0.01 atmospheres. This is for 0.1. This is for 1 atmosphere. This is for 10 atmospheres. This is for 100 atmospheres. If you go on increasing the temperature, you will end up with more and more amount of nickel carbonate. Okay. So that means you can see, if the larger the pressure of your CO, I can even form at this temperature. Right. If you go for 1 atmosphere, if I try to do it at this temperature, I am only still at like what, 50% or 40%. So still the reaction doesn't happen fully. But if I maintain a 10 atmospheres of CO, then my reaction will proceed to more than 95%, right? So that's what we are trying to say, that increasing the partial pressure of your reactants will, the same you can follow just the Litch-Chatterjee principle. That is also one way of explaining. But in terms of pure delta G naught values, so if you increase the partial pressure of your carbon monoxide, you can do the reactions at high temperatures. So this is one point about the carbonyl formation and decomposition. Now the next one is the iodide process. What is iodide process? Here the refining is done by using iodide. So it was first done by Van Arkel and De Boer. Okay. So that's why it is called as the Van Arkel and De Boer process. It is again the same. You form a vapor and then you do the chemical vapor deposition. And it is mostly done for the iodide process is mostly done for your refractory or rare earth metals. Okay. So sorry, rare metals, not rare earth metals. So again, the process is same. You react your iodine with iodine gas with your metal or the impure metal. You get the volatile metal iodide, and this metal iodide is again decomposed to give us iodine, which again can be recycled and reacted with the impure metal plus your pure metal. Now, what is the transporting agent here? Just like carbon monoxide, our transporting agent is the iodine. Again, you can use same the Le-Chatelier's principle. So, same, the iodine formation is favored at high temperatures. Sorry, formation is favored at high pressures, right? Where the decomposition again is favored at high reduced pressure, right? So, if you decrease the pressure of iodine, and again according to Le-Chatelier's principle, if somewhere the pressure drops, so the pressure totally should be balanced, right? If somewhere the pressure drops, the air should travel from there to there. And if the pressure of the composition of iodine drops, then that means your metal iodide will convert into metal to maintain that balance for the reaction. Okay. So that's why you maintain mostly a rough vacuum. That means you can say 10 to the power of -3 to 10 to the power of -4. It's not very high vacuum, okay, or ultra high vacuum. It is, or you can say the medium vacuum, okay, because the rough vacuum is almost -2. -2 atmospheres is -2 bar. It depends on you what you are trying to do. So you need to maintain a -3 to -4 atmospheres. Again, many of the metals will form iodides, but which metal to choose depends upon what type of iodide you are trying to form, right? So because some metals can still form iodide, but these iodides are very stable. They don't undergo decomposition. Then there is no use of forming them, right? Because if you form metal iodide and it is not decomposing, then what is the use of it? Because your final goal is to get pure metal, right? So that means you need to have a smaller cations such that more iodine ions can surround them, and because of this they become unstable. So that means they should show some instability at high temperatures. But some of the iodides will react, but they do not decompose. And if they don't decompose, then there is no use of that process. Right. So again, the same iodide process happens in a single furnace where you charge your furnace with your liquid melt or the metals or fine powder. So and you purge the iodine gas, right? So this iodine gas will react with your titanium or zirconium, hafnium, thorium and form iodides, and these iodides are then again decomposed. So decomposition needs to happen at higher temperatures. So that means if you have a furnace, so let's say this is another furnace. So if you are heating this guy, let's say you are heating this guy, let's say he is at 400 degrees centigrade, then you need to have something, a tungsten filament or something, which should be at high temperature, 1200 to 1100 degrees centigrade, and this can happen by passing current. So we know when you pass current through a wire, there is this term called Joule's heating, right? So the higher the resistance, the higher the heat generation, the large amount of current that you can carry through it, the higher the heat generation, the more the time you give, the large the heat will be produced. Right? The concentration of heat will not change, but the amount of heat will increase with time. production will increase with time. Okay. So that should be remembered. Now at 1200 degrees centigrade, whatever the iodides, the metal iodides that has been formed, because the once formed they become the gases, right? These gases will flow, and because the gases, that high temperature gases have less density, they try to move up, right? So in any atmosphere. Then what happens when they try to move up? They come contact with the high temperature filament, and they undergo the decomposition, right? So this decomposition will lead to formation of a layer here, metallic layer, and again you need to go on increasing the current, because we know that so according to the Ohm's law, if you just take it Ohm's law, V equals to IR, right? For example, if you want to create the same amount of heat, right, and again the resistance will depends upon your resistivity. This is the material constant, you are not changing the material, okay? Resistivity times length divided by area, right? This is a very famous equation. So larger the length, higher will be the resistance. Smaller the area, lower the resistance. Sorry, larger the area, smaller the resistance. Right. So that's why if I try to deposit some metal on it, the resistance will change, and this resistance change should be taken into concern, and the current needs to be either decreased or increased according to the resistance. Okay. Again, let's move on to the final, how the crude nickel granules are. Let's say if you have a nickel sulfide, let's say nickel contains sulfide of 4%, then what we do? So these nickel granules are taken into a pressure reactor. Okay. So let's say I have a pressure reactor, and you maintain it at 180 degrees centigrade of 70 atmospheres. So see, these nickel granules will contain many things: copper, cobalt, right? So then some precious metals also like silver, gold. You need to remove this. So you purge carbon monoxide and you get with liquid carbonyls. Then we evaporate it, do the fractional distillation. So here you have impurities. So what are the impurities are? The copper, cobalt, or some precious metals, AgAu, and some nickel. Residual nickel also will come. Do the fractional distillation. You will have liquid nickel carbonate, and here you have liquid iron carbonate. Okay. So again you do the evaporation and decomposition. Which will result CO for cycle, again recycle, and then you end up with iron. And the same goes here also. You do the evaporation and decomposition. You will end up with nickel pellets and CO for the recycle. So this is how nickel refining happens. And coming to the final refining, okay. These are all the final refining process, and there are other physical refining processes are also there. So in physical refining, we try to take out the impurities and also we try to take out the gases. So the best example is in steel metallurgy, where we do the refining either in BOF or in your electric arc furnace. So BOF is basic oxygen furnace, where you do the oxidation of your impurities. Even in copper also, when we are trying to do the refining process in converting In converting, we do the refining process, right? At last, because you have three stages. One is melting stage. The second is your slag formation stage. Sorry, the first is your slag formation stage. Second is your melting, slag formation, and finally you have oxidation stage, right? Where you purge oxygen in your blister copper, sorry, in your white metal to get the blister copper, right? So, right. So here you have a container in which you have a liquid bath. So first you have a matter, you add the flux. At first you will form a slag. Okay. Then you take it out. Then you end up with the white metal. Why? Because you have a sulfide in it. And then what you try to do, you try to purge oxygen from the sideways, because you do not want to purge oxygen into your liquid metal, because that process is an endothermic process and it will cool. It's not a highly exothermic process. It will cool down your plug, and it can block your oxygen. Okay, so yeah, and this white metal will have Cu2s, copper sulfide, and that will react with oxygen to give you copper plus sulfur dioxide. And if excess oxygen is there, that will react with your oxygen to give you copper oxide, right? And this copper oxide will again react with your copper sulfide to give you copper plus SO2. I'm not balancing these reactions, okay? So this is the whole thing that happens. So finally you will end up with copper and sulfur dioxide. So that's why you will have two different layers. One is your white metal, another is your pure copper melt. Okay, this copper melt still comes as impurity, and because you are purging oxygen, so the copper can take up oxygen. Okay, and there might be some other gaseous impurities that might be present, right? Now, that's why we are trying to do the physical refining. Now, what does the physical refining mean? So, physical refining is nothing but you use the physical properties of metals, bulk metal or the metal, and the impurities to your advantage. That's it. And these are secondary refinings, because the primary refining we did it. Now we are trying to do the secondary refining. In secondary refining, you try to minimize the impurities concentration as low as possible. So that's what in physical refining, again, we use the physical properties of your bulk and the metal and your impurities to your advantage. Now we do the refining of raw steel, okay, to get the different alloys, and or for semiconductors you need very high pure, right? Because if you increase the impurity percentage in your semiconductor, that will downgrade your properties of this current carrying efficiency. Okay. And what are the different physical refining processes? The most usual and common process that's used in steel making and many other processes is the vacuum degassing. What do I mean by vacuum degassing? It follows a simple equilibrium reaction. For example, you have a liquid metal. Let's say I have my liquid metal. Let's say my liquid metal is iron, and in that I have, let's say, nitrogen and oxygen. Let's say we have oxygen in it or nitrogen in it, or even hydrogen also may be present. Now what we are trying to do is we are trying to remove these particles. Now how do you do that? See, nitrogen is remained as N. It remains as an elemental form. To take out from the melt, you need to convert that into gas. Right? So 2 moles of nitrogen should come close together. 2 nitrogen atoms should come close together to form gas. Now if you write this equation, the equilibrium equation, So because the activity, the nitrogen is very much less in our liquid melt, you can directly take the either you can directly follow Henry's law or 1 weight% law. It depends on what type of equation you are trying to take, because the only thing that are going to change are the constants. Okay, so at this you have the partial pressure of nitrogen and the activity of nitrogen square. So this will be Henry's constant for nitrogen in liquid metal times the mole fraction of nitrogen. So for this reaction to be more negative, I mean tending to less negative value, either you need to have this value as more negative, or you can have this value as more negative. This value is fixed at a given temperature, you cannot change it, but this can be changed. How? Either you increase this value or either you decrease this value. We want this value to decrease, so that's what we are trying to do. For that you need to sorry my bad. Yeah, you want to decrease this value and also you want to decrease this value, or you can increase this value. Mathematical way, right? And mathematically, for this term to go more negative, you either increase this value or you decrease this value, or you decrease the numerator or you increase the denominator. Increasing denominator will not make sense, because what we are trying to do is we are trying to decrease the denominator value, right? So increasing is just I mean it doesn't make sense, because you are increasing the concentration of gases in your steel, which will again downgrade your properties when you are this will come in picture when you are trying to do the continuous casting itself. You don't need to go to the application thing, okay, because this, if you increase the concentration of gases in your steel, this will come in when you are trying to do the casting itself, okay. So the material will reject it there itself. So you don't even need to go to application and see where it's going to break or where it's going to underperform. Okay, in solidification itself it will break. So, and again the steels are mostly done via continuous casting, because continuous casting is more efficient when you're trying to handle a lot of hot metal. Okay. So yeah, or you need to decrease the partial pressure of nitrogen. And how do you do that? What is the partial pressure of nitrogen? Partial pressure of nitrogen is nothing but the pressure exerted by the gas on the liquid melt. That is called the partial pressure, or pressure of nitrogen. Pressure of any gas, or the pressure of the pressure of any gas is nothing but the pressure exerted or the force exerted per unit area on any surface. That is called pressure, right? So the same follows here also. The force exerted by your gaseous species, or the nitrogen species on your liquid melt. Now you want to decrease it. How do you decrease it? You just apply vacuum, right? If you apply vacuum, you end up with the less partial pressure of nitrogen. Okay, so that is one thing, and we prefer do to deoxidize steel also. You want to remove the oxygen, because you did the BOF, basic oxygen furnace process, right, where you purged oxygen, so oxygen will also get dissolved in your liquid melt. So yeah. And also deoxidation also happen. Why? Because when you try to decrease the oxygen, or you can even add aluminum or other things where they deoxidize the steel by reacting with oxygen present in your, or eating away the oxygen present in your steels. Okay. Yeah, and then you purged the organ gas, so these inclusions will come up. And the next one is the electric arc melting, zone refining, and finally the distillation. So these are the refining processes. Now let's come into vacuum degassing. So again, I have said before, during primary steel making, which is the BOF, basic oxygen furnace, or EAF, electrical arc furnace. In BOF, You intentionally purge oxygen to oxidize the impurities like manganese, carbon, mostly carbon because 6% is there. That's called the pig iron. You have manganese, carbon, phosphorus, silicon, and yeah, you do the desulfurization, so desulfurization happens there. So yeah, these are the impurities that you will find. Most impurities are these: silicon and your carbon, manganese, phosphor. So these are the main impurities that you will find in steel, and these are the impurities that undergo oxidation in your BOF, basic oxygen furnace. In EF, you either use 90% of scrap, and scrap contains rust, oxygen, nitrogen, hydrogen also will be there. So yeah, which you do not want these things. And again, there is there is other law also which is called as a Sievert's law. So which states that the solubility of a gas in a liquid metal is proportional to the square root of the partial pressure of that gas. Right. So what it means is, here I took 2. So if I divide this reaction by 2, then this will be, and this will become root, and this 2 will go away. Right. So that's what he said. It is directly proportional to the partial pressure of your nitrogen. The square root of the partial pressure of your nitrogen. Lower the value, the better will be your purification. And hydrogen and nitrogen are mostly removed, and also some small extent of oxygen and sulfur also removed under vacuum. Again, as I have said before, whatever the gases present at the bottom, because the gas is in a liquid metal, the liquid atoms are always in motion, right? And so because of that, the gas molecules are homogeneously distributed to some extent. Now let's say this is my liquid melt, and this reaction is a surface interface control reaction. That means it happens only at the surface, not anywhere else, because this is the gas, this is your liquid. So it happens a liquid gas interface. Now what about the hydrogen and nitrogen present here? They need to travel upward. So that's why you need to have some intentional stirring, and this intentional stirring comes from your argon gas. So you have a porous plug and you purge argon such that it will create a turbulence effect like this. Okay. So that's what happens here. And this effectiveness of degassing will increasing in the surface area of your liquid to gas ratio. That means if you have, this is a liquid melt, what about if you have a liquid droplets? Then you have a tremendous surface area increase when compared to a liquid bath. So here this vacuum degassing is much more efficient because the surface area has increased like maybe 10 to the power of 4, 10 to the power of 5 times, right? Yeah. And what are the different commercial degassing that we use are the ladle degassing, the stream degassing, and the circulation degassing. So we will discuss that. So ladle degassing is nothing but the same thing. You have a ladle, right, which is kept inside a vacuum chamber. You take out the air, and that's it. You do the purging with argon. It's a simple process. You have a chamber, you do the vacuum inside the chamber, and you purge argon from downwards. So this will take out whatever the volatile compound, the hydrogen and nitrogen present in your state. And this also, if you try during this process, if you add some reducing elements, the oxygen eating elements. So for example, aluminium. If you add aluminium, the aluminium will react with whatever the oxygen present in your liquid metal. It will eat away the oxygen. It will form alumina, Al2O3, and it will form. And because of this continuous turbulence, this alumina will come to the top and form slag. Okay. So again, this is very strong process where you can do the degassing and also the impurities, the inclusions, which are the oxygen impurities or the impurities that has been present, that also can be taken out. And the next one is the ladle to mold stream degassing. Again, the same theory that they are trying to follow, the large surface area thing. So what do they mean? So they take the liquid metal from ladle and then they pour it in tundish. Okay, and this tundish will pour the steel melt into the mold. That means, let's say this is my chamber, vacuum chamber. Okay, and this is my tundish. Let's say there is a plug here, and I have a steel melt, and here I have a mold, and here I am applying vacuum. Okay. Now if I take out this plug, the liquid metal starts pouring, and here the surface area become increased, right? And because of increase in surface area, the more amount of degassing can happen when compared to your ladle vacuum degassing. Okay. So this is what it does. And again, the last one is a vacuum arc degassing. So it is nothing but you apply arc, and then normally you apply arc. That means you are trying to maintain the high temperature. Okay, and there are many things that happens here. There is a degassing that happens. There are also deoxidation that happens because you are applying arc via electrodes. Obviously there are carbon electrodes, and this carbon will react with oxygen to form carbon monoxide. So yeah, there are different things that can happen here. In the circulation degassing is nothing but, so let's say you have a ladle and which is full of liquid melt. Now you insert some chamber such that, let's say this is my chamber. So you apply vacuum here. Now because of the application of vacuum, because the pressure difference, this, let's say this is a pressure P1 at here, and because of this P0, the drop in pressure, the liquid will rise, and because this liquid will rise, there is again the increase in surface area, so it will take out your gases, again it will flow down. So that's what happens, and this is how the circulation happens from here to here. That's it. Now coming to one of the most important refining process after this degassing, and right, so that is the zone melting or the zone melting or zone refining, you can call any of these terms. So again, simple, the basic theory behind is the high temperature phase so the simple thing, we are heating, okay, so that means there is one, because we are talking about two terms, one is melting, the other is zone. Because let's say the one term is zone and the other term is melting. Zone is nothing but, that means only one part of your whole system is melting, right? Because you distribute your system into different zones, so that means you are only melting one zone. That means only one part of your whole alloy is being melted. Let's say this is my whole part alloy, I am only melting this zone. That is the first part. The second part is I am trying to melt it, right? That means I am trying to form a high temperature phase or a liquid phase, okay? So that means whatever the high temperature phase that has been formed should have high impurity intake. That means the saturation limit of this high temperature phase, or the saturation limit of impurities of this high temperature phase, should be more than your saturation limit of impurities in the low temperature phase. That's the basic theory behind your zone refining. And the best representation of this in phase diagram is like this. This is your solidus line, this is your liquidus line. So at a given temperature, your liquid should intake more amount of impurities than your solid, right? So that is what it tells you. Right. So yeah, we can define, there is this partition constant. Whatever the k that you have, the term value, the k that has been seen in your lecture series is nothing but the partition constant or coefficient. Okay. What is the partition constant? Partition constant is the coefficient, the partition coefficient of liquid and solid. So here you can see, let's say this is the solid, at a given temperature, the composition of a solid with impurities is C0, or liquid. So let's say for liquid it is C0, then for solid it will be KC0. That's it. What does this mean? K is nothing but concentration of liquid divided by concentration of solid. This is what partition coefficient tells you. It is a ratio of your, at a given temperature in a given phase diagram, the partition coefficient tells you about the ratio of the concentration of liquid to the solid. And if K is greater than 1, that means the slope is like this. And if its K is less than 1, then the slope will be like this. Okay. So we need K greater than 1, then the slope is more, greater than 90. Right. So if you measure the slope of this line, which is theta is greater than 90, right? Because this is my 90. This is greater than 90. Okay. So that's how it does. So for example, you have your cylindrical ingot or alloy. So you have, it is mostly done via induction heating. You have an induction coil, which heats only specific part. Okay, so only this zone will be melted. Okay. So that means the impurities will flow into this. Why? Because it is a high temperature phase, and high temperature phase can take impurities more when compared to the low temperature phase. So like this strip or this liquid melting region will move from left to right or right to left. See, you can only do in one direction, you cannot do in both directions. Okay, so if you do in both directions, then the impurities will redistribute, which we do not want. So you do this number of times, or you can have more number of these heating zones, and you just move your rod inside it. So you will form different melting zones, and these melting zones can be, so this is how the rod will move. and because of this the impurities also will move from here to here. So they will finally end up at last stage, which we can cut it out. Right? So this is how the zone melting happens, and either you do the repetition with one induction coil, or you take different number of induction coils, and you just do swing your rod from top left to right. Okay. Now distillation and rectification are also other process. So distillation, again I have said before, it is only possible if your metal forms volatile compounds. If it doesn't form volatile, then it's not suitable for the distillation. So it is mostly done for zinc, cadmium, arsenic and mercury, because they can easily form vapor. They have very high vapor pressure at lower temperatures. So at 900 to 950 degrees centigrade, you can reach up to 700 mm of Hg when you are trying to do the zinc distillation. Okay, so now let's stop discussing on this refining. Now let's move on to the hydrometallurgy process. Now hydrometallurgical process is one of the unit process of extractive metallurgy. Apart from pyrometallurgy, you also have hydrometallurgy, and hydrometallurgy is mostly suitable for lean ores, because when you have lean ores, it is very difficult to follow the pyrometallurgical process, because there are so much amount of impurities comes into picture, right? So that's why whenever people have lean ores, they tend to go to the hydrometallurgical process, then go to the pyrometallurgical process. It's not like they completely avoid. Most of the extractive metallurgical process that we follow are hybrid process. That means it involves all pyrometallurgy, electrometallurgy and your hydrometallurgy. So like more conventional process, for example steel refining, we do not use hydrometallurgy, but there are processes where you can use hydrometallurgy also. But if you are trying to deal with the hematite ore, then we properly go with the pyrometallurgical process itself, because the first starting with comminution, where you do the reduction of size, again you do not involve any hydrometallurgical process. Yeah, in beneficiation process there might be some hydrometallurgical process that can be involved, but still they are not to that extent. And then you come to the blast furnace, okay, or even if you go to the DRI or comet or flash melting process, anything you take, it is a pyrometallurgical process. Then you do go to the refining process, which is steel refining, which is your either BOF, EAF, right? So again the pyrometallurgical, followed by your refining, the vacuum degassing and the other metals that will be taken out, and finally the continuous casting. So most of this contains the pyrometallurgical. So there are very few processes that follows the pyrometallurgical, like iron itself completely. And when you come to copper, you see when you take the chalcopyrite, you do the froth flotation. Again, you involving solvents. Even though there is no dissolution or like acid, but still you are involving solvents, right? Aqueous solvents. Either there will be xanthates or whatever it is. You are involving aqueous solutions, right? And then you go to roasting, partial roasting, which is again the pyrometallurgical process. Then we do the smelting followed by your converting. After converting, you do the purification. Now, how do you do the initial purification? You do by electrowinning. Now comes electrometallurgy. It's not like complete pyrometallurgy, right? You do the electromilling, or there is also natural coal process where you just throw woods into the reverberatory furnace, and the wood will take care of any impurities in there, and it will give you pure copper. And this is very old process, and it is not followed mostly in the world right now. So we directly go to the electrowinning process, okay, to get the pure copper, by where you take impure anode and pure cathode. Again, I have said before, anox red cat. At anode there is only oxidation that takes place, and at cathode only reduction takes place. Okay, so impure anode, that means you have copper and other impurities. So their copper will oxidize, and it will getting reduced at cathode and get deposited at cathode. So whatever the impurities are there, that will be found out at the bottom as a slime. Yeah. Now in hydrometallurgical process, it first again follows the same pyrometallurgy. It first undergo the pre-processing. That means the hydrometallurgical process is nothing but you involve aqueous solutions. First thing is you involve the aqueous solutions. Okay. And how do you do that? Either you dissolve your metallic elements or you dissolve your impurities and you separate metallic elements or separate impurities. Okay. So that is how it happens. And the dissolution is nothing but is a solid to liquid mass transfer process. That means initially you had solid, you dissolve in some solvent, now you have solution. So the whole solid is disappeared. That means the solid, the mass whatever present in the solid will go into your solvent. So that's why it is called as a mass transfer process. Okay. Or material transfer process from solid to liquid. So that is called as a dissolution. And the first thing is a pre-processing. And why do we do the pre-processing? Because if you want something to get dissolved in your solvent, you need to have the property of to getting dissolved or form ions in your solution. And to do that, you need to have certain property of your initial material. So if there is no dissolution, so again the dissolution depends upon two parameters, mostly the pH and the oxidation potential, which can be called as a E. So we will discuss that, oxidation potential of a solvent. Okay. So these two will govern your dissolution of your products or the reactants. So for this to happen, your reactants should be suitable to undergo the dissolution, and for that you need to do some pre-processing steps. So there can be the normal convention combustion process, beneficiation process, the preparation for the ore, and the conversion to soluble forms. Okay. And the best example is the copper sulfide. If you want to dissolve your copper sulfide into your acid, you need to convert them into oxides. So that is the best pre-processing. Then we do the leaching. In leaching, we do the dissolution. You dissolve your metallic elements and take out the impurities. Okay. So for that, you do the next process is solid liquid separation. That means whatever the impurities that are not dissolved will be taken out. And finally, you will have the precipitation, the solution precipitation or solution refining. Okay, this can be taken into, these two processes can be taken into one bowl. So you do the purification and you do the refining. Okay. So now let's see an example. Or yeah. So I will not explain the differences because differences has been discussed very briefly. Now for zinc, for zinc sulfide, first you need to do the roasting process. So you get zinc oxide, then you do the sulfuric acid leaching. That means you dissolve the zinc oxide. Zinc oxide will be dissolved there. And if you are, zinc sulfide is a spellerite. And the chalcopyrite, what we do, you have CuFeS2. So again you do the roasting. Now either you do the sulfation roasting or you do the dead roasting. If you do the sulfation roasting, you will form CuSO4 and will end up with iron oxide. I will write the reaction. Let's say you have chalcopyrite. We have studied that diagram, right? The firebox diagram, where we used oxygen, partial pressure of oxygen, partial pressure of sulfur dioxide, right? So these two parameters and temperature, these three parameters will govern what are the different types of phases that can be formed in your system when you are reacting with sulfides with oxygen. So different reactions. One is the dead roasting, The second is sulfide formation. The third is your sulfates formation, and the fourth is your pure metal formation. Okay. So we will not go into that. Here, if you maintain some partial pressure of oxygen, you will end up with copper sulfate. That means the sulfation roasting. This is, and Fe2O3 and SO2. Okay. So that means let's balance this reaction for the time being. This is 2. Okay, then this will be 2. Okay, then how much? Okay, this is sulfur dioxide. Sulfur dioxide, right? Yeah. So how many oxygen atoms are there? 2, 3, 8, 8, 3, 11, 3. How much is 11? 3, 15. So 15 oxygen atoms are there. Then I need to multiply this guy with. How much should I multiply this by? 15 by 2, right? Yeah, 15 by 2 it is 7.5, 7.5. Yeah. So if you maintain this amount of partial pressure of oxygen and you are okay, I guess I didn't followed up. Okay, there is sulfur dioxide. So the partial pressure of sulfur dioxide should be this much. Partial pressure of oxygen should be this much. If you maintain this ratio, the molar ratio of sulfur dioxide and oxygen in your reaction atmosphere, you will end up with sulfate and iron oxide. Now this sulfate can be easily dissolved in water. So water leaching can be done and you can dissolve the copper sulfate, but iron oxide will not get dissolved in water. So this is one way of doing it. Or you can do the chloridizing roasting. Okay. So the chloridizing roasting again will end up with, let's say I have nickel iron sulfide reacting with NaCl and oxygen. Directly balance, okay, 5.5 to give 2 moles of nickel chloride, Fe2O3, sodium sulfate. Now, and this reaction will end up in the formation of nickel chloride and iron oxide. Right, so this is again one way of doing our reaction. Or you can do alkali fusion reaction also, or you can directly form alkali complex oxides like sodium zirconate, sodium vanadate. Okay, so and for thermal decomposition you can directly do it, or you can just for gold telluride can be decomposed into gold and tellurium. So it's all about the reactions. These are all the pre-treatment reactions. Now leaching reagents can be various types, like you can have acids, less pH, bases, more pH, salts, you want to maintain some neutral reactions, and aqueous chlorine is also there, and etc. Right? And these can result in the dissolution of your metal. Now dissolution of metal can happen either in the ionic state or in a complex oxide state or complex hydroxide state. If you are taking base, then complex hydroxides will be formed. If you are talking about acids, you can have if you have low pH, then you can have different complex anions like sulfate anions, sulfide anions, nitrate anions, and directly the metallic anions itself you are trying to deal with your like high pH values, sorry, low pH, highly acidic environment, right? Now, what are the different types of acids that we normally use for dissolution? We use for copper oxide, we directly use sulfuric acid, okay, the dilute sulfuric acid. And if you have sulfides, if you have oxides, you can use dilute sulfuric acids. And if you have oxides, you can use you need to use concentrated sulfuric acids, because the sulfides are very stubborn and not easy to dissolve. So even there is a need for high temperature also. So that's what you need, both concentrated acids, right? Now the next is the types of leaching or dissolution reactions. Okay. Now you can find different dissolution reactions, right? So if you have dissolution, again I have said before, dissolution can happen either in the simple metallic ion form, or it can happen in more complex oxides or hydroxides. And again, anything can be, so if some compound needs to be dissolved, let's say this is a pure form, let's say the activity equals to 1, then our equilibrium constant will be this one. Okay. Now this is nothing but the solubility product. The higher the solubility product, the easier for the ions to get dissolved, and again the lower the solubility product, the harder the ions needs to get dissolved. Let's take. There is also electrochemical leaching. Electrochemical leaching is nothing but, one is normal leaching. Acidic leaching is via the protonation, where the protons will take the H plus ions will take the electrons and will oxidize themselves. Sorry, they undergo the reduction and give hydrogen gas. So that's what happens in the dissolution of metallic elements, right? So this is a famous reaction. When metal reacts with acid, it gives you salt plus water. No, salt, not salt plus water. It gives you salt plus hydrogen gas. So this is one famous reaction. So that's why you see whenever you try to dissolve some metallic compounds, you see the gas bubbles. Those gas bubbles are nothing but the hydrogen gases. Okay. And yeah, so this the H plus ions present in acid will take the electrons from metal and they reduce themselves to get hydrogen gas. Now in electrochemical leaching, let's say for example the protons are not enough to form this hydrogen. The H plus ions cannot take away or strip the electrons from your metallic atoms. Then what you should do? Then there is a process called electrochemical leaching. Now what does electrochemical leaching does is, you intentionally strip out electrons from your metallic compounds. How do you do that? Just like in electrowinning, you intentionally take out the electrons from the copper atoms present in your impure copper slab or impure copper sheet, right? So the same happens. You intentionally apply positive voltage such that the electrons are taken away, the oxidation happens, and the metal ions give away the electrons, and these electrons can be taken away or taken in the solution by a cap. So that is called as electrochemical leaching. So yeah. Now moving on to and there are different types of leaching. There is in situ leaching, and again this is a new term, in situ leaching, right? In situ leaching is nothing but your, let's say you found out the ore bed or the ore position. So this is my earth surface and this is my ore bed that we have found. Now what we try to do is we drill hole and put a pipe, and again we drill hole at a far position, not a far, farther position, or let's say this is a large hole, and drill other pipe. Now what we are trying to do is, so here I am trying to purge acids. I am trying to flow acids, corrosive acids. Same goes for here also, or dissolution lixiviants, or you can take. And here I am trying to take out. Take out your liquor solution. Okay. So what I'm trying to do here, you have ore. You are not taking the ore out. What you're trying to do is you are trying to just purge the whole ore with your acids, and this acid will dissolve your ore and they will flow here because you are applying negative pressures or less pressure here. Because of the pressure difference, this solution will flow out, and the same goes for here also. Whatever the acid that you have purged will dissolve in the ore bed itself, and this solution, whenever we dissolve something in acids or metallic solution, metallic alloys or compounds in an acid, that is called as a leach liquor. So it's just a scientific, not normal name for language, for like dealing with the solution itself. So you take the leach liquor from here. So that's what the in situ leaching is. And the other like lump leaching, which are directly straightforward. You need not to have like a concern about that. Now let's move on to what are the different aspects of the leaching. So again, I have said before that two important things that define your dissolution of metal ions or the metals into your solution to form metal ions depends upon your pH, and the next one is the oxidation potential. There is this, either you take oxidation, so let's say you got a value of oxidation potential as it is measured in volts or millivolts depending upon the value, so it is represented as E for now. Okay. So if, for example, if I am trying to like dissolve my iron in acid, okay, so this is the reaction I am trying to do. Right, now I cannot write directly, right? So delta G, if I want to write the equilibrium reaction, you cannot directly write, right? Because we do not know how to write for activity of electrons, right? So that thing we didn't learn actually. So for this we actually derived one equation called as Nernst equation. So Nernst equation is mainly used for this type of equations. So for example, if I try to even write this equation, that will be written as delta G will be equals to delta G naught plus RT ln Q. Q is my, again, reaction quotient, which is depends upon the products and reactants. And there is this reaction for delta G and electric potential. Now what is delta G? Delta G is nothing but the energy, right? Now what is E? E is nothing but the potential difference. What is potential difference? Potential difference is nothing but the amount of energy required to move a unit charge from one end to another end in a given electric field. So that is called as a potential difference, right? So potential difference definition is nothing but it is the amount of energy required to move one charge, a unit charge, in an electric field from one point to another point, right? So that can be written as, so divided by number of moles if you are trying to like move a charge under a different potential difference times the Faraday's constant, which will be equals to your delta G, right? And we know Faraday's constant is nothing but 96,500 coulombs, or it is nothing but the charge contained by 1 mole of electrons, right? So we know 1 mole of electrons is nothing but 1.6 into 10 to the, oh sorry, this is the charge, my bad. So charge, single charge of an electron is 1.6 into 10 to the power of minus 19 times 1 mole of electrons is nothing but 6.023 into 10 to the power of 23, which will be indirectly, I mean, if you do the multiplication, it will come 96,500 approximately. It is a big number, but it is approximated to 96,500. So then delta G will be equals to NFE, right? So delta G, because it is a negative, please remember. delta G will be equals to minus NFE equals to, and for delta G naught it will be minus NFE naught plus RT ln activity of reactants divided by activity of products. Right. So what is my activity of products divided by activity of products? This 2 is written here. This 2 is nothing but the number of moles of electrons. So E will be equals to E naught minus RT upon NF ln activity of products. What is my activity of products? Fe, activity of Fe plus 2 divided by activity of Fe. If I take activity of Fe equals to 1, then it will be activity of Fe. Right? So we know R is nothing but 2 point, again if you ln, it is a natural logarithm. If you want to write it in base 10, that will be 2.303, right? So this can be written as, and R is nothing but 8.314, and at room temperature or 298 standard conditions, 298 Kelvin, this will be E equals to E naught minus 8.3, okay, let's multiply it, 8.314 times 2.303 times 298 divided by 96,500. Let's do it. 2.303, 2.314, mistake, 2.303 times 8.314 times 298 divided by 96,500. So it is 0.059. Okay. So it is nothing but 0.059. 0.059 divided by N divided by log of activity of Fe plus 2 in the solution. So this is how we involve when we are trying to, when we have electrons in your reaction or oxidation reaction. And if it is only the pH, then it is directly written as the delta G equation. Okay, so from this we build a parabox diagram. So turbo diagram, again it is simple. So if you take the different reactions of iron and at different oxidation potentials, and you draw a phase diagram between the potential and the pH, and depending upon the reaction it will result in different regions, and different regions will be dominated by different products. For example, for zinc, this is like this. Let's say this is -1 volt, and this is like pH almost 8. So here I have Zn plus 2, here I have ZnO, and here I have ZnO2 minus 2. And please remember, we do this dissolution or the electro dissolution reactions if our whatever the regions lie in between our hydrogen evolution reaction and oxygen evolution reaction. Hydrogen evolution reaction is nothing but your dissolution reaction, and the same goes for oxygen evolution reaction also. So this is oxygen evolution reaction, this is a hydrogen evolution reaction. If it lies between in these two, then we are good to go with electrodeposition or electro dissolution. If it doesn't, then either we have hydrogen evolution reaction or oxygen evolution reaction, and we will not end up with the dissolution. Okay. So this is about parabox diagram, parabol diagram, and you can directly do it. And finally, you have bacterial leaching. So I am not going to discuss much about it because you can directly refer to it. Okay. So and then finally we have solution concentration. So solution concentration you do either by the carbon adsorption or solvent extraction or ion exchange. So carbon adsorption, as name itself suggests, carbon adsorption happens when certain metal bearing ionic species are effectively getting absorbed on your carbon or activated carbon surface. So you need to have metals which can react with which have a property so that they get absorbed on carbon surface. And the next is ion exchange. Ion exchange is nothing but for example, you have two solutions. Let's say one is organic solution, another is your solvent aqueous solution. So organic solution has some anions or cations, and aqueous solution has some cations or anions. And in ion exchange, there goes the exchange of either cations or anions. That's it. You mix this aqueous and organic solution, you agitate them such that cations go from organic to aqueous, or anions go from organic to aqueous. That's it. There's simple exchange of cations and anions. So that's all about ion exchange. And finally, I have the solvent extraction. We will discuss this in next lecture. Okay, the final session. In solvent extraction, at one end you have. I will draw it. Actually, I'm expanding it. Let's suppose I have an aqueous solution and an organic solution. This organic solution will only take some metal ions from your aqueous solution. Okay, so far so good. Same as anion exchange, but instead of anions, you are directly taking the metal ions. Okay, there can be formation of coordination compounds, or there can be formation of multiple ligands. Okay, so any of this process can happen. Now this is called as a pregnant solution. Pregnant solution is nothing but it contains your metal ions that you are interested in, and this organic solution again is reacted with another aqueous solution. So what does it does? This organic solution will strip your metal ions from your aqueous solution. Okay, and this organic solution again can be reused. And this aqueous solution is either precipitated, dried. Again, the same thing happens. You can either do the precipitation reaction, or you can do the drying, or you can do the distillation reaction. It depends upon the property of the metal ions present. So this process happens like many repetitions, such that you strip all the metal ions from the solution. So yeah, that's it for today's session. We will meet in the last session where we will explain a bit more about solvent extractions and some other topics. Alright, okay, so thank you.